the more confident you have in your cooking. Why? It tastes better, right? So the thing about strength of materials is you have to have the confidence. Okay. Once you have the confidence, I want you all to have that confidence. Okay. I can see some of you do already, which is good. Okay. Once you have the confidence, okay, then you are not worried. Okay, should I take the analysis from the top? Should I take from the bottom? The answer is the same. Okay. Right. But I want you to try on your own. Okay. The solution manual is good and bad, right? Okay, the solution is there. I just follow it. Okay. Yeah, but you not have that confidence. Okay. Right. So if we tabulate all the data now, the shear stress at A is equal to the shear stress of B, which is equal to I think it was 0.98 P over I. The shear stress at point C, which is thus discovered, is 1.778. Right. So from here, what we realize that stress C is much greater than shear stress at point A and at point B, right? So therefore, shear stress at C is equal to 1.778 V over I, and this is equal to 10 times 10 to the power 3. Is it 10? I can't remember now. Let me search. Yeah, 10 times 10 to the power 3 psi. Okay, so the V over I ratio is equal to 10 power 3. Okay, divided by 1.778 is equal to 5.624 times 10 to the power 3. I'll do it again. Okay, 10 power 3 divided by 1.778 is 5.624. So therefore, the shear stress at point A, which is equal to the shear stress at point B, this will be equal to 1.778 multiplied by not 1.778, it's equal to 0.98 multiplied by 5.624 times 10 to the power 3. Okay, so 0.98 times 5.624 power 3 is equal to 5.55. I get 5 point, is it 0.98, 5. Okay, so it's 5.511.52, okay, psi. Okay, so this is your answer. So what is so unique about this problem, as you can see? Okay, so this problem, go on, I have to put down, my bad, pardon me. So this is your example number 2. What is so unique about this problem? Why I like this problem? Because the structure, right, combines box beam and wide flange analysis. Okay, that's why I like this problem. Okay, you can see what is the difference with the two. Okay, if it's just if I just give you I beam or box, easy now, right? Now you can combine. Okay, so I'll tell you this. A lot of universities, okay, for this topic, they usually just skip this topic. They don't like to teach this topic. Why? Because this topic is very abstract. right? Why abstract? Because the formula is still what? VQ over IT. If you have this formula without these rules, okay, without knowing these rules, it's confusing as hell. Okay, trust me. Okay, I've been confused before. Okay, now I'm going to make matter worse for you now. Okay, we're going to try a different problem. Okay, we're going to try a different problem. So before I go on, anyone, any question, please? Anyone? No.
I have a question.
Okay.
Sorry.
Yes.
I have a question regarding like the thin wall and thick wall analysis. It seems that depending on the geometry of the structure, they can have similar results or they can be very different.
Yes, absolutely right. Okay, you are absolutely right. Like what I've shown you before, right? Like over here, right?
Mm.
At point A is different, but at point B, if you do if let's say the geometry is exactly the same, but you do different analysis, the results can be exactly the same. Okay.
So why do we do one over the other then?
So it's geometry. If the wall is thin, you have to use thin wall analysis.
Okay.
Okay. If the wall is thick, you use thick one. It's purely geometry based. If you are not sure, okay, go for thin wall. If you are like, because the stresses will be what? Higher, yes or no?
Yeah.
Right?
Yeah.
Right. Okay.
Okay.
Now I will do example number 2. In fact, the question was a good lead in to example number 2. Okay. So example number 2 is this question. And can anyone tell me why I like this question? Anyone? What is the, so if you look at the structure like this, right? Okay. Let me show you what's going on first, okay? And then you tell me why. I think then you all will know why I love this problem. Okay. We know that the shear force V is coming from here. So this problem is very similar to what we've just done. Again, given that the maximum shearing stress is 75, okay? Determine the stresses at point A, point B, point C. Very similar, okay? And anyone tell me why? Anyone tell me why I love this problem? Anyone?
Maybe because of the geometry of the diagram is symmetrical?
No. It's symmetrical because what I told you is symmetrical for now. Okay. But why do I like this? Han Chong, you're right. Combination of what? You're absolutely right.
We have a box beam wide flange analysis as well as the thin and thick wall analysis. Is that
No, it's not. It's not. It's going to be white flange. Okay, for sure, it's going to be white flange. Okay, but why this problem is interesting is thick and what? Combined analysis. Okay, thick and thin wall combined analysis. That's why I love this problem. So once again, if you understand the concept well, okay, which I believe all of you can understand the concept well, this question is easy. Okay, and I'll show you why. Okay, so let me copy this diagram first. So until where is thin wall and until where is thick wall? Right? Like, oh yeah, where is it thin wall and where is it thick wall analysis, right? Okay. there's only one part that is actually true. There are 2 points, not 1 point. That is thin wall analysis. That is point B and point C. So from here to here, I'm going to color in yellow. Okay. From there to there, down here is white flange, thin wall analysis. All right. And then when you have this section coming in, which I'm trying to, you can see it's coloring in blue, right? Yeah, I'm partial colorblind, can't really see at all. Right. So over here, we switch to thick wall analysis. And all he has to do is thickness, right? All he has to do is just the thickness. Okay. So now so first of all, if we construct the shear flow, okay, the shear flow is controlled by the web, right? So the shear flow will go down. So you can see over here, you have a terminal over here. You have 2 terminals over here, right? Terminal 1, terminal number 2. So that's why it's a white flange. Yeah, you can apply. So hold on, you can apply for the whole section. Even at point A, your answer will still be right because of the wall thickness. Okay, you can, but you cannot apply thick wall for the whole section. Okay, you cannot apply thick wall for the whole section. Wait, Azam, I have to be careful over here because if we apply thick wall analysis, yeah, you still consider the both area, okay? But yeah, at point A is thick wall analysis and thin wall is still the same, like what I mentioned before. At the centroid, whether you apply thick wall and thin wall, the answer will be the same, okay? Glad that you're applying what you have just learned. Okay, now, so now we're going to find the shear stress at point C. So we are going to apply thin wall. Okay, we apply thin wall. White flange. Analysis. There's only one Q. And now the thickness is 0.01 meter. Okay, that is the thickness. So the area that we are going to focus on is this area now. Okay, it's that area. So the Q at point C, the width is 30, the depth is 10, the centroid is 80, right? Because it's 160 divided by 2 minus by 10 divided by 2. Okay, so this will be equal to 80 minus 5 times 10 times 30. So it's 22.5 times 10 to the power 3 millimeter cube. and we have to change this to 22.5 times 10 to the power minus 6 meter cube. Okay. So from here, your shear stress at point C is equal to V over I